Everybody, today we are going to take a look at chapter 2, and specifically we're going to work some problems from chapter 2. So I'm going to try to work 4 problems, or at least get you started on 4 problems from the homework. And so if this vodcast is too long, you'll be able to break it up into different problems. So you'll see them on the document cam. And I'll try to keep them clearly labeled so you know which problem I'm working on, so that you can fast forward if you need to do that. So the 4 problems that I would like to work today are 114. Oops, gotta widen this out a little. There we go, maybe. Okay, problem 114E, and then 269, 242E, and 273. All right, so let's start with 114. 114 says, the force required to compress the gas in a gas spring a distance x is given by this equation. And the equation for force is this constant divided by x, which would be the distance of compression raised to the k power, where the constant is determined by the geometry of this device and k is determined by the gas used. Okay, so the exponent is based upon what gas we're compressing, and the constant is based on the geometry of the device. So it says one such device has a constant of 200 foot-inches to the 1.4. So in other words, for this particular device, we would have 200 units being inch to the 1.4 pounds of force over x time raised to the 1/4 or 1.4 power. Determine the work in BTUs required to compress this device from 2 inches to 7 inches. So x sub 1 is 2 inches, and x sub 2, or x sub final, is 7 inches. Okay, so the first thing we need to do is to use the idea that work, the differential of work, is equal to the force acting through some distance. Okay, so in this case, the distance that we're acting through is x. So if we then say that the differential of work is equal to force, and I'm going to use this equation. Now, even though we have inch pounds, I'm going to leave the units off for now, but remember that work, if a force is measured in newtons or pounds of force, and work is measured in force times distance. So in this case, it's going to be inches. So when we do our integral, we're going to come out in inch pounds. Then we're going to have to convert inch pounds into BTUs to get the final answer. Okay? So anyway, at this point, we're going to have 200 over x to the 1.4 del x. Now if I integrate this, and I integrate this between 7 and 2, or take the antiderivative if you prefer, we can see then that the work done from 2 to 7 inches is going to be, I'm going to pull the 200 outside, the integral from 2 to 7, and since this is in the denominator, that's actually x to the minus 1.4 dx, or del x. This just indicates that it's an inexact differential, but the work is exactly the same. So then we have 200. When I integrate or take the antiderivative of this, I get x to the negative 0.4 power divided by negative 0.4 from 7 to 2. Okay, and that's just because I increase. Remember, like if I had x squared, took the integral of x squared dx, it's just x to the 3rd over 3. That's all I'm doing right here. It's just that we're with decimal powers instead. So we end up with 200 times, let's just pull this out as well, negative 0.4. And this would be x to the minus 0.4, evaluated at 7 and 2. So if I take, just to find this number out front, 200 divided by negative 0.4, oops, I have the wrong number, 200 divided by negative 0.4, this is 500, negative 500, and then I would have x, which is 7, raised to the minus 0.4, minus 2 raised to the negative 0.4 power, and let's see where my button is for that. Don't have too much opportunity to take exponents of this form. What are you? 7. And that's going to be my just tens. Do I have a y to the x button? You tell I'm not used to working with this calculator.
You want to borrow mine?
If you, or you could just do this for me, how would that be? Would you mind? If you would just take 7, raise it to the negative 0.4 power, and tell me that number.
It's 0.459.
0.459. And then, is it negative or positive? It should be positive,
Yeah,
right?
positive.
Okay, then minus, what is 2 raised to the negative 0.4 power?
It's 0.757.
0.757. Okay. So now I'm back to, I'm on good calculator footing again. 0.459 minus 0.757. So my parenthetical quantity is a negative 0.298. And I multiply that by negative 500, and I get negative 149. Excuse me, positive 149, because this is negative and this is negative. So the work done from 2 to 7 inches of compression is 149. That would be in pounds of force inches. All right, so now I need to convert to BTUs. And I know that there are 778 foot-pounds per BTU. And I know that there are 12 inches per foot. So if I convert, if I do 1 foot over 12 inches, that will convert me to foot-pounds. And then I have foot-pounds on top, so I have 1 BTU per 778 foot-pounds. That will get rid of the other units, and I'm left with BTUs. So the amount is 149 divided by 12 and divided again by 778. So that number is 0.015959 or 0.016 BTUs. Okay. So do you have questions about that? Does that make sense?
Yeah, that makes a lot more sense.
Excellent. Yeah. Right. So there's a couple of things here, and one is, of course, the theory that work is equal to that the differential of work is equal to F dot dx. And so then once you have the equation for F, you can find the antiderivative, and since it's a definite integral, you can solve for the amount, and then you have to do the conversion. So yeah. So good problem. Good problem. Your classmates will thank you. Number next, we're going to do, these are not in numeric order, but the next one I want to do is 2-69. So let's take a look at problem 2-69. I'm also choosing this because it doesn't have an E after it, which means that I most likely will not have to do English unit conversions, and we'll be able to work in the SI system a little bit. Okay, so large wind turbines with blade span diameters, put it right here so we can take a look at it, right, of over 100 meters are available for electric power generation. Consider a wind turbine with a blade span diameter of 100 meters installed at a site that is subject to steady winds at 8 meters per second. Taking the overall efficiency of the turbine at 32% and the air density to be this, determine the electric power generated, determine if steady winds at this speed for 24 hours, the amount of energy, and the revenue. Okay, so here's sort of the ideas. First of all, power is equal to energy per time, right? Or if we find power, we can multiply it by time. Oops, you want to probably see that. Let me widen this out again. This is, all right, hang on. There we go, that's better. So if we have power and we multiply it by time, then we can have energy. So here's what we have going on. We have a wind turbine, this is sideways, and the diameter of this turbine is 100 meters. And it's being impinged with wind at a speed of 8 meters per second, and the air density is 69, 1.25 kilograms per cubic meter. So what we're really talking is a volumetric flow rate past this wind turbine. In other words, if we were to draw it sideways, or frontwise, I guess the first one is sideways, what we really have is an area that's a circle that is 100 meters in diameter. This is referred to as the swept area. Okay? So the swept area for the wind turbine is a circle, pi d squared over 4, pi times 100 meters squared over 4. And so that number is 100 squared times pi divided by 4, or 7,854 square meters. All right, so what's happening is we have a volume of air going past this wind turbine, or blowing through the wind turbine every over a period of time, I guess I would say. So the volumetric flow rate, because this is normal, right? The speed, the wind is perpendicular to the blades. So the volumetric flow rate is going to be the area, the swept area of the blades, times the velocity of the wind. Or the volumetric flow rate is going to be 7,854 square meters times 8 meters per second. And if I multiply those two numbers together, I find that the volumetric flow rate of air passing through my wind turbine is 62,832 cubic meters per second. All right, so what do I know about this? Well, I know that if I had a force operating through some distance, that I would have some differential of work. And I also know that power times time is equal to energy, right? Which is some form of work. In this case, we're taking wind energy and converting it to electrical energy, but our efficiency is only 32%, which is actually quite high for a wind turbine. So it's 0.32 or 32%. So how do I convert a volumetric flow rate of air into power? Well, if you think about this, what we're really looking for, if we're talking about power, let's go back to units of power. Power is measured in energy per time, which is force times distance per time. Okay? And if you think about a force per time, you can say that a force, let's go back to Newton's second law, force is equal to mass times acceleration, right? So force per time must be equal to mass per time times acceleration. Okay, this is just kind of to get some units out of this. But basically, we could also say that force divided by acceleration is equal to mass. Okay? And in the case of what we have here, we could say that mass is equal to weight divided by g. All right, so what am I dancing around here? It's the idea that we are taking a kinetic energy of wind and we are converting it into electrical energy. So what we're really talking about is here for our mass, we're going to have to get, or for our volumetric flow rate, we're going to have to get it into a mass flow rate before we can really work with it. So a mass flow rate is going to equal a volumetric flow rate times a density. So we can start here and say then that our mass flow rate of air going past our turbine is going to be the volumetric flow rate of 62,832 cubic meters per second times the density, which is 1.25 kilograms per meters cubed. So what happens then is our meters cubed cancel out and we're going to get kilograms per second, which is a mass flow rate. So I take 62,832 multiplied by 1.25 and I get a mass flow rate of 78,540 kilograms per second. All right. Now, what we're really talking about then is if we have a kinetic energy from the wind and we convert that into an electrical energy, but only 32% of the kinetic energy from the wind, because that efficiency, becomes electrical energy. And since we're talking about rates, we can say the same thing about power. We can say KE dot, or the rate of kinetic energy, is going to equate to the power that we're going to be able to derive from our turbine. All right, well, if you think about it, kinetic energy is 1/2 mv squared. And so rate of kinetic energy could be 1/2 times mass rate, m dot, times v squared. So we have an m dot, and we have a velocity. So we can multiply these together. I'm going to show you one other thing before I finish up here, or kind of tangential, but I'm going to go ahead and work this out. So my rate of kinetic energy is 1/2 times my mass flow rate, 78,540 kilograms per second, times my velocity of 8 meters per second, quantity squared. Now I'm going to go ahead and work this out. What I would like to show you is that mass flow rate involves volumetric flow rate, which already involves the velocity. Okay? So if you look at this basic equation, this has a velocity in it. So we have something times velocity times the velocity squared. The upshot of this is when you have a wind turbine, and other kinds of turbines as well, velocity is king. In other words, rate of kinetic energy available to you is based on the cube of the velocity of the wind. So the velocity of the wind is the utmost dominating factor in how much power you can get out of a wind turbine. All right, but I kind of wanted to go through this process with you. But in general, you can always say that the rate of kinetic energy from a wind turbine is equal to 1/2 m dot v squared, but m dot itself is equal to v dot times rho times v squared. I'm going to put a vector over this just to indicate that we're talking about velocity. And I should make this pointy too, just let's do that to keep our symbols straight. Okay, and then volumetric flow rate is the swept area times the velocity. So this is equal to, we have 1/2, and then we have pi d squared, which is the swept area, over 4 times the velocity times the density times the velocity squared. And if you put this all together, that the general equation that we come up with is that the kinetic energy rate available from a wind turbine is pi d squared over 8 times the density of the air times the velocity of the air raised to the 3rd power. And this in general is an equation for the computation of wind power, or kinetic energy available. The efficiency is where it comes in, how good the turbine is, but this is like an upper limit. In other words, you can't, and you actually can't even get this much, but even theoretically, you can't get more than this amount of energy out of a wind turbine. So I just wanted to kind of stress the importance of the velocity. All right, so if I go back to this, I've got half of my calculation done, and I can take my 78,540, multiply it by 8 squared, which is 64, and divide that by 2, and get this number, which is 2513280. So 2,513,280 kilogram meter squared, right, per seconds to the 3rd. That is a wretched unit for power. It's true, but it's wretched, so we need to find out what that really means. That's where we come back to our Newton's second law. So let's say force is equal to mass times acceleration, and in the SI system, we measure force in newtons, mass in kilograms, acceleration in meters per second squared. So rearranging this equation to solve for kilograms, I can say then that a Newton second squared per meter is equal to a kilogram. And this is the substitution that I want to make in this unit in order to get my units to come out in something usable. So a kilogram, let's go ahead and do this, is equal to a Newton second squared per meter. So I'm substituting that in right there. Then I get meters squared, seconds to the 3rd. And if I cancel, what I see is that I'm left with this unit being equivalent to a Newton meter per second. So that a Newton meter is a joule, and a joule per second is a watt. So isn't that sweet? We're back down to it. All right, so that means that the rate of kinetic energy of this wind turbine is 2,513,280 watts, or 2.5 megawatts. Now, the turbine is only 32% efficient, so to get the power, I will have to multiply that by 0.32. So that number multiplied by 0.32 is 804 249.6 watts. Okay, now a watt is, as we said, this is a unit of power, and so the question asks us, taking the overall efficiency to be 32% and air density to be this, determine the electrical power generated by the wind turbine. This is the first answer. This is the electrical power generated by the wind turbine. Now it says if this steady wind of 8 meters per second blows for 24 hours, how much electrical energy? Energy is measured in joules, and we know from the first part of this work that power times time is equal to energy. So I need to take my power, 804 249.6 watts, or joules per second, and I want this to occur over the course of one day. So there are 3,600 seconds in an hour, and 24 hours per day. So if I do that cancellation, this is per hour. I don't know why I put, because I started with minutes. Okay, so my hours cancel out. And so I take this number, multiply it by 3,600, multiply again by 24. That is how many joules of energy I will produce in a day. So I take 804, 249.6, multiply that by 3,600, multiply it again by 24, and I get that my energy in 24 hours is 6.95 times 10 to the 10th joules. And I need to get that into a better form. We'll talk about that. There are 10 to the 6 joules per megajoule. Sorry, so I could say 6.95 times 10 to the 4th megajoules in 24 hours. And then the last part is, what is the revenue generated per day for a unit price of 0.09 cents per kilowatt hour? All right, so now we get to talk about kilowatt hours, which is also a measure of energy. So we get to discuss this. One, I'm just going to say kilowatt is a measure of power. Kilowatt hour is a measure of energy. So it kind of looks backward, because when you see the time introduced, it seems like it would be a rate, but it's not in the denominator, it's in the numerator. So it's a backward unit where we talk about power, which is the rate first, and then we talk about energy. So let's go back to our power that we're generating. We have 804 I'm going to do this, I could do it from here, this megajoules, but I'm going to go back to the power just to do the units so that you can see how this works out. All right, so we start with our power of 804 249.6 watts. And we know that we have 1,000 watts per kilowatt. So the first thing that we see is that we can take that number and we end up with 804.3, just to round off, kilowatts. That is the rate at which I'm generating power. 804.3 kilowatts is a kilojoule per second. And there are 3,600 seconds per hour, and there are 24 hours per day. Okay, so if we want to be in kilowatt hours, let me think about this. Kilojoules, kilojoules. Okay, I did that right. So basically then, I want to do just a kilowatt hour. Let's do this. Kilowatt, I always have trouble with this. How many? It's 24, but why am I doing this backward? 804 0.3 kilowatts, I guess times 24 hours, I guess that's it, is equal to that number of kilowatt hours. I always do this too complicated, I apologize for that. So the answer is 804.3 times 24 is 19303.2 kilowatt hours generated in one day. And I'm told that the price is 0.09 cents per kilowatt hour. So if I take 0.09, not 0.09 cents, $0.09, that's 9 cents per kilowatt hour, and I multiply that by 19303.2 kilowatt hours, I just take that value, multiply it by 0.09, and that gives me a yield of $1,137.29 per day. Yeah. So if I change this into seconds and hours, then I have to get rid of the seconds, and so you end up multiplying by 3,600 and dividing by 3,600. And I always started off that way. I don't know why. It's just like something that I always do, and I always overcomplicate it and do it incorrectly. All right. Do you have any questions about that one?
So, like, you know how you gave out the wind power, like the perfect wind power equation?
Yes.
So if you did that equation and multiplied it by 0.32, would that give you still the wattage?
Absolutely. Well, that would give you here's the equation for the kinetic energy rate from a wind turbine. And to answer your question, if you multiply that by 0.32, that gives you the amount of power you get out.
Okay.
So in other words, you're losing 68% of the power in the process of generating the power.
Okay.
Yeah. So that's great. Great question. Anything else?
No.
All right.
Yeah.
All right, let's do one more. It looks like we have time for one more problem. So we have 42E and 73. Okay, 73 is really excellent problem. This is how hydropower works. Basically, you have water, and you have a mass of water, rho GH, right, that is a potential energy, and it converts to a kinetic energy at the bottom of the dam, and that goes through a turbine, which spins a magnet and creates electrical energy or electrical power. So in this particular problem, it says the water behind Hoover Dam in Nevada is 206 meters higher than the Colorado River below it. So that means that our height is 206 meters. At what rate must water pass through? So what kind of a rate are we talking about? Maybe a mass flow rate or a volumetric flow rate? I don't know at this point, but we're going to figure it. It doesn't really specify. But at what rate must water pass through the hydraulic turbines at this dam to produce 100 megawatts of power? So what we're really looking at is the same thing. We want a KE times this efficiency, which here is 1.0, is equal to the electric power. And but we're saying that it's 100% efficient. So in this case, KE dot is equal to power. All right, well, where are we going to get the KE dot? The answer is from the falling water. So conservation of energy tells us that the potential energy at the top, the rho GH of the water, is equal to the kinetic energy, the 1/2 mv squared at the bottom. Okay? So we need to convert this into rates. So if we think about what mass is, or density is, it's mass per volume. Volume then is equal to mass divided by density, and volumetric flow rate is equal to mass flow rate divided by density. Okay, so I'm just going to write this as rho is equal to m dot over v dot. All right, and when I say that, we're talking about volumetric flow rate. I need to be careful with that. So in this particular equation, we're interested in this energy being converted into potential energy. And if we talk about m dot over v dot GH is equal to 1/2 m dot, this is velocity squared, isn't it? Well, from our previous problem, we also determined that KE dot, we can cut directly, well, let's go ahead and do it this way. We know that if we look at this equation, then we can basically say that m dots will cancel out, which is still not all that useful to us, but we can start at this point. And if we wish, we want to find out what that m dot is though, but it doesn't really matter, I guess. Let's start at the bottom instead. We're talking about, instead of talking at the top, it says at what rate must water pass through the turbines to produce 100 megawatts. The power that we get out is 100 megawatts. And that is going to be equal to 1/2 m dot v squared. Okay. So let's go ahead and think about what this power is. Megawatts is 10 to the 6th watts, which is a joule per second, which is a Newton meter per second. Okay? And a Newton, once again, when we did our work with Newton's second law, we know that a Newton is a kilogram meter per second squared. So this unit is equivalent to a kilogram meter squared per second to the third. So if we are talking then about mass flow rate, if we say this is in kilograms per second, we're left with a meter squared per second squared, right? So this would be the mass flow rate times the velocity squared, just like we had here. Okay, so then we have to think about what the velocity is going to be at the bottom. And if we can plug that in right here, then we're going to be able to solve for mass flow rate, aren't we? Okay, so just based on energy, potential energy, rho GH equals 1/2 mv. I get my v straight, squared. So that means that my v squared is going to be rho GH times 2 divided by mass, or v is going to equal the square root of 2 rho GH over m. Okay, so we know h, which is 206 meters. We know g, which is 9.8 meters per second squared. And we know density of water, which is about 1,000 kilograms per meter squared. And we don't know the mass. That's what we're actually looking for, okay? So if we say then, you know what I'd rather do here is solve this for mass, wouldn't I? That would be more logical. Okay, so if I say that, let me go ahead and do this. rho g h times 2 over v squared is equal to mass. Okay? I really want to do something different here. MGH, this isn't, that's what's going on. Oh my goodness, I cannot, I just was, I don't know what's going on here. This is the weight. That's where I started. I was like, there's something wrong with my equation. Okay, so kinetic energy is m mass times gravity times height. In other words, that. Okay, so then this is 1/2 mv squared. Masses cancel out here. So my g times my h. I was like, what am I doing wrong? All right, so there we go. So my velocity is just going to be this. That makes it so much easier, doesn't it? When you use the right equation. This is meters per second squared, and my height is 206 meters. That equals my velocity. So I get the square root of 2 times 9.8 times 206. Which is the square root of 4037.6 units would be meters squared per second squared under the radical. So when I take the square root of that, I get 63.54 meters per second is equal to the velocity. Okay, so the velocity at the bottom is 63.54 meters per second. The power then is equal to the mass flow rate times the velocity, or mass flow rate is equal to power divided by velocity. Okay, so my power is 100 megawatts, 100 times 10 to the 6th watts, joules per second, or Newton meters per second, divided by my velocity of 63.54 meters per second. That's going to give me something different. And we're going to find this. Maybe that's my, let me look at my units here. So this and this cancel, this and this cancel, and I get newtons. Doesn't even make any sense for a unit. So let me think this one through. If I do that 100 divided by 63.54, and I get 1.57 newtons. Okay, that doesn't make any sense. So let's go back and take a look at what I did wrong here. This should just be m dot gh. See, it's haunting me again. So there's none of that going on. So m dot gh is equal to that. Okay, so my power then, because my kinetic energy would be 1/2 mv squared, my power would be 1/2 m dot v squared. This should still work because a mass flow rate would be in units of kilogram per second, meters squared per second squared. Can I make that be a megawatt? A kilogram meter per second squared is a Newton meter per second, which is a watt. Okay, over here, kilogram per second, yeah, my units should be the same. So I have something weird in my math. Let me go ahead and just do this over again. Just this last part, not the whole problem. Don't worry, I'm not going to do that. All right, so I start with the idea that power is equal to 1/2 m dot v squared, velocity. My power is 100 megawatts. Multiply that by 2, divided by the velocity, which is 63.54, right? 54 meters per second quantity squared should be my m dot. So I get Yeah, I missed something here too. 2 times 100 equals, divided by 63.54 and divided again by 63.54. And that number turns out to be 0.049537 in units of megawatts per meter squared per second squared. So second squared comes up here, equals m dot. Okay, so now we just need to resolve this unit. A megawatt is 10 to the 6th watts. A watt is a Newton meter per second. Yeah, here we go. This is what I want to avoid doing. So then what I also want to do is a kilogram meter per second squared is a Newton. So I'm going to write that instead of that. Kilogram meter per second squared, meter second squared, second meter squared, second meter squared, kilogram per second. Hallelujah! We got some units that look good. So I get m dot then is equal to this number times 10 to the 6th kilograms. So 1, 2, 3, 4, 5, 6. 49537 kilograms per second squared. Okay, so we need to go back to that basic idea. First of all, we need to use the right equation. You do not put rho where it's m, and so that was the first thing. And then when you find power, we're converting 100%, so we can find a mass flow rate, and then we have to resolve the units in order to get our final answer. All right. Do you have any questions about that?
No, that makes sense now.
Does it? Okay. On the last problem, this is 73. I don't know that we're going to have time to work it out, but I'll start it, and at least we'll get it moving in the right. Oh, that was 73. 42 is the one. Okay, so we'll go to 42, and we'll get it started. Problem 242. A water pump increases the water pressure from 15 psia to 70 psia. Okay. Determine the power input required in horsepower to pump 0.8 cubic feet. That would be a volumetric flow rate. 0.8 cubic feet per second of water. Does the water temperature in the inlet have a significant effect? The answer is no, as long as the fluid remains liquid. It changes. If it turns into gas, pumps don't work well with two-phase fluids unless they're designed that way. So as long as you're staying in liquid water, you should be just fine. All right. Now this sort of speaks to an equation which is called the Bernoulli equation. And what Bernoulli says is that there are basically 3 types of mechanical energy that can be measured in different units. But there's pressure, energy, kinetic energy, and potential energy. And this is actually where I was getting the rho GH thing. So there are different forms of the Bernoulli equation, but they and all that they're really based upon for incompressible flow like this is the units. In other words, the different forms of the equation are just different because of what units we're measuring the pressure in. All right, but for incompressible flow, Bernoulli says that v squared, this would be velocity squared over 2, plus gz, which is a position, plus p over rho is a constant. All right, so on one side of the pump we have a lower pressure of 15. On the higher side of the pump we have 70. and we're going to have to put some power into it to do that pressure increase. So basically, we don't really have a kinetic energy. We don't really have a potential energy. What we're really saying is that P over rho on the inlet plus the energy put into the pump is equal to P over rho on the outlet. Okay? And if you look at these units, what you're going to see, if pressure is measured in pounds of force per inch squared, rho in the US customary system is in slugs or pounds of mass per cubic foot. I'm going to take a different unit just because it's a little bit hard to convert slugs and pounds of mass and pounds of feet. Let's just look, since this is a consistent equation. G, it would be in feet per second squared, and Z would be in feet. So this comes out to be feet squared per second squared, as does this. So we're really looking at something that's going to come out in feet squared per second squared. But if you want to just look at it in terms, and what is feet squared per second squared? That's another part of the issue, because how do we incorporate this idea? Okay, well, we're talking about power, so we have power as a rate. So we can look at each of these terms as a rate, and we can say a delta P is equal to some sort of a rate based on that factor. So we have a cubic foot per second, and we want to get it to feet squared per second squared. And so we're going to have to resolve units. At that point, I ran out of time, so I do apologize. But this is kind of the basic idea of where you start. So you're taking a delta P, which is the 70 minus the 15, and you're expressing that as a power requirement. Okay? And so this value is a volumetric flow rate. So where we were talking about rho g h or something like that, rho times g is actually equal to a density. But when you start working with that, you'll be able to see where that comes out. All right? And if you don't, give me a call and we'll work it out after class. Tomorrow, or not tomorrow, I won't be on campus tomorrow, but we can do that. I think if you play with this, you'll see how it comes out. All right? All right. Well, that's it for today. Yeah, glad you came. It was fun to work some problems. So this will be posted up to our Moodle page, so you'll have it for reference. And now you'll know where to fast forward, and you can just look at what you need to look at. So,
perfect.
All right. Thanks. We'll see you next time.